Okay, section 11.2 is on page 747, talks about series. This is the introduction to this, the remainder of the chapter. So 11.1 talks about a sequence, 11.2 talks about a series or series. So if I sum up the terms of a sequence all the way to infinity, I'll call that S sub infinity, or simply either an infinite series or series will do. One geometric series, one series in specific we are more interested than most of the other series are the geometric series. Geometric series, you take a term, you multiply by a number, you multiply by the same number to get the next term. Arithmetic you add, we're not interested in arithmetic yet. And the general form of an arithmetic sequence, a geometric sequence, a sub n is normally, oh, I messed up. Let me fix that. A sub 1, there we go. My mistake. I knew something was wrong from the beginning. There we go, got it. And if this is the case, if you have an infinite sum and the absolute value of this common ratio, r, you find r by taking any term divided by the previous term. If this r happened to be between -1 and +1, this infinite sum will equal a finite answer. The very first term, you decide what the first term is by plugging this n in, or looking at the very first term on the list, divided by 1 minus whatever you're multiplying with every time. That's crucial, because if they say find the sum, add those up. If you want to find an infinite sum, we can only find two sums in this chapter. One of them is a geometric series. I want to get that out of the way. And the other one, we use this method called telescoping. I'm going to save that for the next video. For now on, I'll focus on all the geometric series and get those out of the way. Starting off, and this is going to be on page 755. Directions: determine whether the geometric series is convergent or divergent. If it converges, find the sum. That's the key term. By them stating find the sum, and they only do that in this section. Find the sum, they're telling you this is either geometric, or we're going to use this other trick called telescoping. I'll show you what that means in a minute. Actually, in a few minutes. So, if I start with this, determine whether the geometric, so they're telling me this is geometric, I don't have to check. I need to figure out what r is. R is take any term divided by the previous term. And you could check. If I multiply this by 3/4, I'll get 9/4. And if I multiply this by 3/4, I'll get 27/16. So absolute value of r is less than 1. Therefore, this infinite sum will be the very first term divided by 1 minus r. The very first term is a 4. R is 3/4, right? And if you clear the fraction, you could leave the answer like that on the test out of mind. That would be 16 divided by 4 minus 3, which is 1. And there it is. This infinite sum will equal 16. Looking at the next problem, again, they told me this is geometric. I'll take r, which is any term divided by the previous term. That is 1/4. And since that's less than 1, this infinite sum will equal the very first term divided by 1 minus r. That's a fine answer for the test. Multiplying by 4 to clear the fractions. That will be 8/4 minus 1, which is 3. So this infinite sum will be 8/3. And if I look at the next problem, number 22, and if I look at r, if you could tell by looking at it, you're in good shape. If not, list few terms. Throw a 1 in, 5/pi. Throw a 2 in, 5/pi squared. And now think of what is it you are multiplying with every time. Or take any term divided by previous term. I know r is 1/pi. 1/3.1 is less than 1. Therefore, this infinite sum will be the very first term. The very first term divided by 1 minus r. This is a fine answer. If you clear the fraction, that would equal 5/pi minus 1. And if I look at the next two problems, number 24, I look at this and I need to combine this a bit. Now, I never mentioned if r is bigger than 1 or equal to 1, this series will diverge, meaning the sum will be infinite. So I have to manipulate this a bit, and I'm going to take a 3 up front and say that's the series n equals 0 to infinity of 3 over negative 2 to the n. So this is me using algebraic manipulation. I know that r is negative 3/2, which is bigger than 1, right? Therefore, diverge. I can't find the sum. And I'm going to look at 26 next. Let me move that just to make it look nicer. Here we go. And the same deal. I need to use some algebraic manipulation to really get r out of this. That's 6 times 2 to the n, 2 to the 2n, times 2 to the negative 1 over 3 to the n. Since all of these are multiplied, I'm looking at 6 times, and isn't this 1 over 2? And this is 2 squared over 3. So this is 3 times the series n equal 1 to infinity of 4 over 3 raised to the n. And I noticed that r is 4/3, and that's bigger than 1. Therefore, this sum diverge. Next problem, number 12. Number 12 says, in the directions, look at a graph, sketch this on a graph. We're not going to do any graphing utilities. We're just going to use the traditional method. So I'm going to ignore the directions on number 12 of graphing and list the first few terms or look at the graph. We're just going to find whether this series converge or diverge. And if it converge, find the sum. So I'm going to say this is 7 to the n times 7 to the 1 over 10 to the n. I'm going to take this 7 up front, and that's the series n equal 1 to infinity. And I can combine those by using algebra to 7 over 10. And here I notice that absolute value of r is 7 over 10, which is less than 1. You know what? I could fit a problem right there. Let me just put this down here. No, let me leave it here. It's okay. Then I'm going to say, well, this sum, and don't forget that 7 is going to equal 7 times the very first term. To find the very first term, throw the n equal 1 in. N equal 1, I'll get 7 over 10 over 1 minus r, which is 7 over 10. On a test, this is a fine answer. You could clean that up and say that's 7 times 7 over 3. So 49 over 3 will be this infinite sum.
Okay, the next set of problems, we need to get a couple of theorems out of the way. So, well, I'll show you the problems already. Let's talk about this part. So here, we have a theorem that says, if a series is convergent, then the limit as n approaches infinity of a sub n equals 0. Right? It doesn't say much really, and we're going to use that barely, but I could use this in section 11.1. If I have a sequence and I can't seem to find the limit, if I can show that the series converge, then I could conclude that the limit of the sequence part equals 0, and therefore the sequence converges itself. I'll talk about that when we get to 11.6 and refer back to some of these problems. This is a 5-star theorem. We don't have that many of those. Test for divergence. It is really derived from this. This says if this is true, then that's true. So A implies B. The conclusion I can get out of that, not B implies not A. So if it rains, there must be clouds. If there are no clouds, it cannot rain. If this limit does not equal 0, so doesn't exist, if it doesn't equal 0, if it equals 0, you're out of luck. If it doesn't equal 0, you assume that This is not true. And there's only convergence and divergence, which means that will diverge. And this is, we're going to prove that in the coming sections. Here they say this is harmonic and it diverge. We're going to prove that when we use the integral test, B-series, a few other ways, limit comparison test. I'm going to show you that this diverges multiple ways. For now, you memorize that 1 over n diverge, end of discussion. Now, directions in the book vary greatly because they run back and forth between graphing and non-graphing. So, I want to look at, and yeah, you guessed it right, I want to do all the evens, every even problem in this section. So, they're asking a lot of different things. To us, this is what we want. Determine whether the series converge or diverge, and if it converges, find the sum. So what am I going to do? I'm going to really check test for divergence. And where do I check that? On every problem in this chapter. Every problem. I take the limit as n approaches infinity of cosine of n, and what that takes you back to L'Hopital. This does not exist because of oscillation. And since it's not zero, it diverges by test for divergence. 30. If I take the limit as k approaches infinity of k squared divided by k squared minus 2k plus 5, I could use L'Hopital twice. I could divide by the highest power term of the denominator. That would equal 1, which is not 0. Therefore, diverge by test for divergence. Test for divergence helps a lot if it works. Here, well, the limit as n approaches infinity, that's a 0 and that's a 0 out of luck. If it equals 0, it doesn't mean anything. But I recognize that this is geometric. R is negative 0.2 is less than 1. Very good. This first piece is going to equal the first term divided by 1 minus r. This second piece, r, is 0.6. That is less than 1, so that converges. That's going to equal the very first term, that n equals 0, equal 1 in there. That's going to be 0. So 0.6 to the 0 is 1 divided by 1 minus r. This is a fine answer on your test. Here, well, what am I going to do with that? I'm going to take the series n equal 1 to infinity of 2 to the n over e to the n, a bit of algebra, and that's going to be the series n equal 1 to infinity of 2 over e to the n plus 4 over e to the n. Here, r equal 2 over 2.71 less than 1, that converge. But here, r equal 4 divided by 2.71 bigger than 1, therefore diverge. The limit as n approaches infinity of that will give me a 0, so that's useless. And on number 36, if I take the limit as n approaches infinity of 1 over 1 plus 2 over 3 to the n, keep in mind, this is going to 0 out because that's exponential decay. That's going to be 1 over 1, which doesn't equal to 0. Therefore, diverge by test for divergence. Something that we're going to have to start quoting on every problem. If you say geometric, then we're fine. R is used with geometric. I'll point that out once I get to the next video. This is geometric. And R is radical 1 over radical 2. An absolute value that's less than 1. Therefore, we know it converge. And the sum, if I add this, s sub infinity, is the very first term. Remember how to find the first term. You plug that value in. Divided by 1 minus r. There it is. Everybody's happy. How about here? Well, this is the series n equal 1 to infinity, 3 over 5 to the n, plus the series n equal 1 to infinity of 2 over n. This is harmonic. For now, you're going to say harmonic. Therefore, diverge. And if I look at